In this video, we're going to analyze, or I'm going to walk you through the analysis of another data set, which is a bit more sophisticated than the previous data set that we saw. So here we are looking at a baseball data set. We have data based on these 6 variables. Player gives us the name of the player. PRIPOS refers to the specific position in which they play. That is when they're not batting. They could be a pitcher, left field, second base, first base, pitcher, and so on, catcher, and so on, shortstop. Hits refers to the number of hits they achieved when they were batting. At bats refers to the number of turns they got for batting. And then we have two other columns, player number and PRIPOS number. These are redundant in the sense that a player number corresponds to a particular player name, and primary position number refers to the values in primary position. So our actual analysis includes only these 4 columns. So our goal is to determine whether individuals differ in their batting ability. That is, across the individuals, do they vary in terms of the ratio of hits to at-bats? The other thing we want to investigate is whether there is a difference in the number of hits achieved, in the ratio of hits achieved to at-bats based on the position. So we are comparing things across positions, and we are also comparing things between players. So the thing that makes a data set somewhat interesting is that unlike in the coin flip example, if we think each individual representing a coin and each position representing a particular mint from which the coin is derived, in those examples we can assume, or we can conduct the experiment such that all of the coins are flipped the same number of times. However, in this case, these are actual data, so if you're familiar with baseball, I'm not very familiar, but from what I understand, not every individual gets to bat the same number of times. For instance, some of the players are chosen primarily for their ability to serve as a catcher or as a pitcher. So they, when it comes to batting, they probably are not going to be the first picks. On the other hand, folks who are picked for their batting ability might play in one of these positions in the field. They could also, for instance, play in multiple positions. So what we are trying to do is model the variation across all these. So there are variations in terms of number of at-bats. There are some who have batted more, there are some who have batted less, and there is variation among the individuals and also among individuals within each of the positions. So the way we would model this is, let me pull up the thing over here, is like this. So we have the individual. Each individual observation's likelihood is a Bernoulli, but it is contingent on a given subject and a given category. And the theta for a subject given a category, that is, subjects belong to a category. Subjects are the individual players and categories are the positions. This is modeled as a beta distribution with 2 parameters, omega and kappa, for each of the categories. So if we have, say, 15 types of players, I'm making it up, I don't know if it's really 15, but let's say it is 15, we would have 15 such beta distributions, one for each position. And then we are saying the omega c and the kappa c for each of these can be modeled by two separate distributions. The omega is modeled based on a beta distribution. The kappa c is modeled based on a gamma distribution. Each of these is for each of the categories. And within the category for the beta distribution, we have a certain omega and kappa. So the omega here refers to the overall omega aggregated at the level of all categories. And the omega over here, WC, refers to the aggregate of omegas for all the individuals within each category. So we have players who play in categories, and all these categories are at the top level. So within each category, let's say we have category 1, we have certain number of players. So their theta is modeled based on the omega for that particular category and the shape parameter, the concentration for that particular category. Similarly, this would be omega 1 and kappa of 1. For category 2, it would be omega 2 and kappa 2 and so on. So we are modeling things within each category, and also we are aggregating them and saying these values are constrained by this overall distribution. So the omega 1, omega 2, omega 3 up to omega 15, because I said there are 15 categories, all those omegas are derived from this beta distribution, this grand beta distribution, which has is what represents the omegas. Similarly, the kappa, the kappas that we have here, so kappa 1 for first category, kappa 2 for the second category, all of these are modeled based on a gamma distribution with a given value for the shape and the rate parameters. Meanwhile, this particular thing that we have here, sorry, that was for the group level, right? The omegas, looks like I conflated a few things. Let me redraw these quickly. I apologize for the confusion, so let me quickly redraw this to clean things up a little. Okay, so let's try this again. We have each category, and we have the overall thing over here. So each category has its own omega and kappa. And these are used for modeling the thetas, that is the ratio of runs to at hits for each of the players. So we have player 1 who has a particular theta derived from these two things. We have player 2 who also has these two things. We have player 3 and so on. Similarly, we have, let's say, player 29, player 30 and so on. So each of these players belongs to only one category. So their ratio of hits to at bats, which is same as the proportion of heads to number of flips, it's the same analogy. So these are distributed. So this omega c is distributed by an overarching beta distribution, and that is defined by an overarching omega and kappa, this particular thing. Similarly, this is also governed by the same thing. We are looking just at the omegas, by the way. Over here we have omega 3, and this is also governed by that. Now there are kappas also. So these kappas are governed by a gamma distribution. So the kappas modeled by that, this thing is modeled by that, this other thing is also modeled by that, and so on. Now these themselves, this overall beta distribution which constrains the values that these individual omegas can take, that is modeled at a higher level as follows. This at the higher level is a beta distribution, and this kappa at the higher level is another gamma distribution. So there are, the first is embedded in the second is embedded in the third, and third is embedded in the fourth. So there are 4 levels over here for theta when you trace through the omegas, and for the kappa you have 2 levels, one over here and the other over here. So why do we have so many levels? What is the idea that we are trying to capture? The idea that we are trying to capture is that, firstly, the ability to hit varies across players, firstly. And this variability is can be further categorized across the different places where the different places on the field where the players play when they're not batting, when they're on the pitching side of the game. So because we have conceptualized our data as consisting of the variability both at the individual level and also aggregated at the group level, we have these two things. And we are also saying the overall group ability can also be modeled as something that is derived from across the group as a whole. So the group as a whole feeds into the individual's estimates based through the intermediary layers. The intermediary layers refer to the distribution parameters at the category level. That's why we have so many layers. Now when you're looking at a different data set, you may or may not have as many layers. You may have a fewer number of layers, or you may have additional layers. Really, your specific conceptual problem, the way you have collected your data, the way you have conceptualized the data collection even, that is what drives how you model. So there's no one-size-fits-all approach that we can use. It so happens that in our case we have data related to their primary position, and we are saying we are going to model the distribution of hits to bats ratio using a combination of variability at the individual level and at the category level. Now if we for some reason did not have data related to where they play, all we had was data related to subject and that is the player and their actual hits to at bats ratio values. If that was all we had, then we wouldn't have this extra layer. Our model would look let me keep scrolling. Our model would look like this. We'll have all the thetas, well, like this. Now because we have categories also, we are factoring that information also into our estimate, because we believe that players do differ in terms of their ability, and that difference can be modeled based on the category to which they belong, the category of fielding or pitching or catching to which they belong. Okay, so and here's what the model looks like. It looks sort of complicated, but as Krushki keeps repeating, so long as we draw our diagram correctly, translating this into code is going to have a one-to-one mapping. So for instance, we start over here at the level of the data, and we say that y, we'll talk about why we jump to z over here in a minute, but I'll talk about that once I've explained all of this. So this data is represented as a distribution with theta for each of the subjects, and this is true for all of the n number of subjects, which is what we're doing over here. And also theta of a particular subject is modeled as a beta function. That is, we have modeled this based on theta. We are modeling theta as determined by a beta function with two parameters, omega at the category level and kappa also at the category level. So this is how the thing looks, the beta distribution looks, right? What we have done, if you remember, is rather than having just the two shape parameters a and b, we have converted a and b into the model mode and the concentration parameter Kc. And that's what we have over here. The direct observation is modeled as theta. Theta is modeled based on a beta function of omega and kappa parameters, and we are saying for each of the categories, omega varies for each of the categories. Omega varies as a beta with higher up omegas and kappa, so we call them omega 0 and kappa 0 to refer to what we have over here. And this kappa c is modeled as kappa minus 2 of a given category plus 2, and this thing is modeled as the gamma, which is what we have over here. So this thing is really this thing over here. And then this omega 0, which is the high level thing, this is modeled as a beta function. And note that we are using the shape parameters of 1 and 1, implying that we are using a uniform distribution. That is, we are using a very diffused prior on this category level omegas. So we are saying within category there are going to be differences, but across categories we do not really know if one group is better than the other. We are just assuming, or we believe, that groups are going to be different, but we don't know who is going to be better or worse. So we are going to say that these omegas all come from a uniform distribution. And then kappa is modeled in the same way as it is done at the previous level, using the shape and rate parameters. And once again, the shape and rate parameters are computed using the function that I told you about previously. This function. So we are going to plug in the values of mean equals 1, standard deviation equals 10. So mean value, this is considered to be a generic vague distribution. So we are using those, and we are obtaining these values, and we are plugging them in. Okay, so that is our model. As you're building your models, the biggest challenge you would face in the modeling is firstly determining what is the nature of your outcome variable. So in this case, you look at these numbers and say, well, these are continuous values. Perhaps you could even compute a ratio. But if you have the ratio split into its original numerator and denominator form, you can see that hits as a proportion of at-bats is similar to the ratio of number of heads out of a total number of flips, which means this can be modeled using a Bernoulli distribution, which is why we are using this approach over here, this thing over here. Similarly, we can also go one step up and say the Bernoulli's thetas are distributed using a beta distribution. We have seen this before, because a beta is going to help us represent, say, a uniform prior. It could also help us represent a more concentrated prior, something like this, and so on. And after we have figured these two out, we can say there's also the notion of the category playing in. So I'm going to add the extra layer of modeling these things at the category level, and the category level parameters are going to be modeled by something higher up. So after you figured out how to represent your y variable in your model, you have to determine what is a good way to represent the predictors. Of course, in our case, since we have only categorical nominal predictors, and one of these can be seen as being subsumed, that is belonging to one of these categories, we can see a nice hierarchy here. And this particular engine, which is already given to us readily by Krushky, we can use it. So when you're doing this for your final project or any other data set, you have to see which among the variety of models that are described in our book comes close or is exactly the same as what you have in mind. So what the model that you're going to build for your project is going to be a variation of one or more models that you see in the book. So I'll talk about this in some detail when talking about your discussion forum, but this is the idea. Now, once you have figured out how to set up your model, if you have been able to identify the engine which looks similar to this kind of model, you can quickly apply that engine without having to write all of this code yourself. But eventually you might come across a fairly sophisticated data set with lots of variables, and some of which might have hierarchies, in which case you have to spend some time carefully building the conceptual model, which is this figure. Then once you have that, you will follow the examples and write up your model string like this. Okay. So once that's done, the other thing we do is in the not the engine, but in the driver code, as I'd like to call it, that is so this is the engine which has the actual genm, cmc and all these other functions which do the actual computation. We have the other one which makes use of this. So over here we set up our data. We also run the mcmc method and all that. One of the things to keep in mind is this thing over here. Of course, we want the diagnostic, so we'll make use of that. But here's where things are going to be different for each of the engines. In our case, for instance, we are trying to compare categories 1, 2, and 3. Similarly, we're also going to compare subjects 75, 156, 159, and 844. So these correspond to, if you're doing the plotting, these correspond to pitcher, catcher, and first base, 1, 2, and 3. And these individuals, I think, actually we have more individuals than what we have over here. So you can, in the plot, pass the names directly. So how does JAGS or R in this case know how to look them up? It knows how to look them up by looking at the actual values of these variables. So we need to make sure that the values that we are specifying here, these values, are exactly the same. They should match in terms of case, in terms of spaces. Everything has to be an exact match. Otherwise we are going to run into errors. So we need to specify these things. The other things we need to specify would be our engine expects these specific variable names. So z name for the outcome, n name, subject, s name, and c name. So these correspond to the specific. So z and n, you can think of them as corresponding to number of heads and total number of flips. S refers to the subject and C refers to the category. So we have to specify in the dataset that we read which ones correspond to which ones, and that's what we are doing over here. So once we have set all these things up, we need to run this code. I'm going to pause the video here because running this code is going to take several minutes. So let me pause this and come back. So I'm showing you some execution of my code. What I did was I previously ran the code, so I'm just using that to quicken the demonstration. If I ran the whole thing from scratch, it would have taken several minutes actually. I don't remember the time, but it had taken me several minutes. At this point, let me talk about the use of the z instead of y over there. And another thing to keep in mind is that we are using a binomial distribution as opposed to a Bernoulli distribution. This was explained on page 249 under the section titled Speeding Up JAGs. So Krushky describes why the use of the binomial distribution instead of the Bernoulli distribution is useful. This is a slightly technical thing, a technical description. So what I'm going to do is I'm going to read the paragraph that's on page 249 at the bottom. So essentially what is happening is, rather than treating our study, well, maybe I won't read it directly. Let me see if I can explain it. So rather than treating our experiment as a series of as a series of flips of a single coin, we can envision our data differently. The way the data are generated differently. So we could say that we want to look at our data as consisting of multiple experiments where each experiment consists of multiple flips of the same coin. So what do I mean by that? So in the binomial distribution, we assume that we are going to flip the coin a given number of times, let's say n equals 10. And we're going to see how many of these flips turn out to be heads. So if we conceive our data generation process in that form, then we are going to come up with a probability distribution which looks like this. P of generating, let's say, I'm writing from the book over here, theta s times ns is n s choose zs times theta s raised to times 1 minus theta s raised to 1 minus that. So by changing the way we conceive things, we are going to look at the same data, but when it comes to running the MCMC, previously we would have run multiple runs for one per observation. So if we had, say, 20 observations in our data set, we would have performed MCMC 20 times. But by reconceiving this, we can achieve a speed up in JAGs, because JAGs would now treat this rather than as 20 individual experiments. It will look at it as one experiment with 20 instances, 20 observations. So what really happens here is that rather than having 20 random walks, you can have one big long walk and reuse the values from it for estimating the posterior. This doesn't work always. It works only in certain instances. For instance, where our prior on a particular parameter can be reconceived in a slightly different way. So if we have a Bernoulli likelihood function, for instance, defining how the data are generated, we could recast it as a binomial distribution, and that would result in a significant amount of speed up. The exact reasons of the exact derivations are covered a little bit in page 249 and a little bit on page 126. So go through that, and if you have more questions, please do ask me. I'm going to focus more now on the actual results, how to make sense of the results. So it looks like my code is still running. It's going to take a few more minutes, I suppose. Let me walk you through what I have over here. Okay, so we have done that part, and here's the plot MCMC. So we are producing various plots based on the specific inputs that we are sending. So for instance, this is used for coming up with these comparisons. So I'm comparing pitcher with catcher, and I'm checking to see whether the posterior of this difference is close to 0. Another way of saying this is, are the posteriors for pitcher and catcher the same? If they're the same, then we know that pitchers and catchers do not differ in their estimated probability of getting a certain number of hits when they go to bat. What we observe here, particularly when we are looking at this thing over here, is implying that there is a difference, and pitchers have a lower estimated value of number of bats number of runs to at bat ratio than catchers. It's I can reach that conclusion by looking at the negative value of the mode. So the value of number of runs hit to number of bats for pitchers is less than the same value for catchers, and this value has this aggregate value is negative 0.016. Similarly, if we look at catcher minus first base, catcher seems to be performing better than first base also. So, well, actually, catcher seems to perform worse than first base. First base has a higher amount of value. And we can look at the HDI intervals over here also, and nowhere do we see the value 0 falling in the 95% highest density interval. So indicating to us that there is a non-zero difference. So if we were to rank these three groups of individuals, we'd say that pitcher is smaller than catcher, and catcher is smaller than first base. So of the three, first base individuals seem to be making a relatively higher ratio of runs achieved to at bats. Now we can't do an exact subtraction of mode of this from mode of that to obtain pitcher minus first base. We have to compute the difference once again. But since we did not ask for it, we did not get that difference. So we can't directly subtract those. It does not make sense to do that. Now let's look at some other differences also. Here we are comparing specific individuals. So we're comparing Kyle Banks, who played at first base, with Bruce Chen, who was a pitcher. And it turns out that the difference of thetas, once again, well, the mode is 0.124, which means in this case Bruce Chen has a, let's see, Kyle Banks minus Bruce Chen is positive, which means Kyle Banks blanks is higher than Bruce Chen, and this difference is 0.124. And if you look at the difference, the 99% of the posterior is greater than 0, which means roughly about 99% of the estimated um, distribution of the mode of this difference is greater than 0. So there is a lot of difference. So you can say there's a 99% aggregate probability which is in favor of Kyle blanks. Similarly, if we compare these two individuals, Shin-Soo Choo and Ichiro Suzuki, we find the value to be negative, which means that Ichiro Suzuki is having a higher mode of the ratio than Shin-Soo Choo. They look very similar, but it's also negative. That is, this is slightly higher than this. Now if you pay attention to the HDI, the 95% HDI, you see that 0 falls roughly right smack in the middle. So while there is a difference, it's not substantial because there is 50%, 51% of the distribution to the left of 0, and there is about 49% to the right of 0. So based on what we are seeing over here, we can say that the estimated ratio of runs to at bats. These two individuals do not differ significantly. They are very close to each other, and roughly 50% of the time one is higher, roughly 50% of the time the other one is higher. So we can't really say who's better or worse. They are equally good. Here on the other hand, we can say that Kyle Blanks is better than Bruce Chen. Now looking over here, we can see that Mike Leakey is better than Wandy Rodriguez, and this difference is in favor of Mike Leakey. You can also see, while the difference is small, 98% of the estimated distribution is greater than 0. That is, it's favoring Mike Leakey. So we can say that while the difference is 0.087, it is substantial in that 98% of the distribution is greater than 0, favoring Mike Leakey. Analogously, if we look at Andrew McCutcheon versus Brett Jackson, both of whom play the same location, same position, we can see that 99% of the distribution is greater than 0, which means Andrew McCutcheon is having a better estimated posterior than Brett Jackson. So there is a difference, and this difference is substantial. So even though they are playing at the same field, at the same position in the field, Andrew McCutcheon is having a higher ratio of runs to at bats than Brett Jackson. So here again we are comparing the same positions, pitcher and pitcher, but Mike Leakey is better than Wandy Rodriguez. So we are doing a within category comparison here, whereas here we are doing across category comparison, first base versus pitcher. Here once again we are doing a within category comparison. So here there's no difference, here there is a difference, so is there over here, and here there is none. So while there are going to be individual differences both within group and between groups, on an aggregate we need to figure out what the overall mode is, to see what is the overall, if we take a look at everybody, what is the aggregate mode, and this is what we have. these are for the omegas, omega 0, right, at the top level. And at the top level, the overall aggregate estimate of this ratio, where was that ratio? Runs divided by at bats. That ratio is 0.23. But within each category, we have these individual omegas. Right, these individual omegas, you can see some of these are 0.25, there's 0.123, there's 0.259, and so on. So each of these individual groups has their own omegas. That is the highest likelihood expected value of this ratio, and you can see they all differ. Some of them are similar to each other. For instance, these two folks, or perhaps even these two folks, right, second base and left field. And some of these are fairly different. For instance, pitcher versus, let's say, third baseman, or even pitcher versus, say, right field. In fact, pitcher seems to be very different from a majority of these. And some of these might be somewhat different, some of these might be very different. And all those pairwise comparisons can be made by specifying those to be our requirements in the output. Okay, so what do we learn from all of this? What we learn from all of this is that the hierarchical structure is an expression of how we think about the data, should be modeled meaningfully, and how the model description captures the aspects of the data that we care about. So the reason we model things both at the aggregate level as a whole and also aggregated at the group level, at the category level, is because we firstly had access to data like that, and secondly, we believed that there might be a difference. But we also were not sure whether the difference is favoring one as opposed to the other, which is why we put up a gamma, well, not gamma, where was that? A beta of 1, 1 on the aggregate. So the model that we build is based on how we conceive the kinds of questions, the answers to the questions that we want. Also note that if we did not categorize by position, the estimated abilities of the pitchers would be much more noticeably pulled towards the model abilities of all non-pitchers. That is, if we did not include the middle layer, everything would be compared or constrained from this overall big distribution of theta. So all the thetas would be estimated based on one big omega, and that omega is something that represents the entire group. Also, if we did not categorize by position, the estimated abilities of any two players with identical batting records would also be identical, regardless of their position. So in these graphs that we have here, we saw that individuals, even though they're playing at the same position, do differ in their estimated ability to get this ratio. Their estimated ratios are different. However, if we did not have the category, all of these folks would be pulled towards each other. So the comparisons of pitchers with pitchers is not going to be as nuanced because we are pooling all of the data together. So when we have these kinds of hierarchies that we can conceive of, and we also have data which gives us this information, we should actually include those things in our model, because that way we can avoid what is known as shrinkage, that is, all the lower level parameters being pulled towards the aggregates mode. So the nuance is lost if we do not include a hierarchy when including a hierarchy actually makes sense. Now, neither of these is incorrect. That is, including the categorical layer versus excluding it. Neither of which is supposed to be superior to the other or is more correct than the other. The what matters is the question that we are asking and whether we have the data in our data set to address that question. So in our data set, if we did not have this column of primary position, then we wouldn't have been able to do the nuanced analysis such as what we have over here, and we won't know any better because we don't know that aspect of that facet of our data set. Now quickly let me pull the diagnostics, just a sample of the diagnostics to see whether these things are converging or not. Let's look at the overall omega, for instance. There is the caterpillar thing over here. We also see that the autocorrelation is fairly close to 0, but there is a little bit of cause for concern in that the estimated sample size is somewhat small. It's less than 10,000. And we also see, if you notice, that the shrinkage factor has gone up away from 1. So there is a bit of cause for concern here. These are diverging, and you'd also see that over here. So how do we rectify this? Let's see how the other ones look. The other ones are all, well, at least this one seems to have converged, but the other omega one is once again not converging. It's you can see it's at least some of the chains are not at 1, and this is just above 10,000. So what might help is if we ran our MCMC method for a longer period of time. That is, if we increase the amount of sampling we did from the posterior, that would likely produce less autocorrelated errors, more ESS, and so on. Okay, let me round this off by looking at the last thing over here. So we perform, just to reiterate, we perform pairwise comparisons that are meaningful to use depending on our research questions. So a comprehensive set of comparisons of the posterior probability distributions along with the posterior distributions are saved to a CSV file. So for instance, the figures that we produced are not all, but some of them. If I pull up this CSV file over here, you will see the estimations of all of the parameters in our model, all the individual parameters, I should say, all the omegas, all of the kappas. Now these are, remember, these are the category omegas. And there's the overall omega, there are the category kappas, there's the overall kappa, then there are the thetas. These go up to 948 because we have 948 observations in our data set. So each theta is estimated for each player, which is why we have so many. Now we have done only a few pairwise comparisons, right? These are the aggregates at the category level of the modes, and these are the aggregates, these are the comparisons of the modes at the individual level. Now there are 948 players, which means doing every player by player comparison is going to produce a lot of computation. So that's why we have not done that. Similarly, even if you're doing a pairwise comparison at the category level, you'd still have several comparisons to do. So That's why we have not done that either. But if you want, you could, but you'll have to specify all of those in as options when you're running this. So with that, I'm going to conclude this video, and in the next video I'm going to talk to you about the application assignment and the discussion forum. But before that, let me quickly summarize. This has been a fairly long video, so you might be tired by the time you got here, so let me quickly summarize. There are a few key ideas here. One is, by looking at the data set, if we identify a situation where one of these variables can be subsumed under the other, that is, one of these fits into one of the categories over here, we have what is known as a hierarchy in our data set. So we combine that with our modeling approach to produce a multi-level model, a hierarchical model, and we estimate the parameters accordingly by specifying the appropriate priors on each of the model parameters. The way we specify the priors is based on our understanding of the data, and when we believe we don't have enough prior knowledge, we use a diffuse prior, which is similar to what we have over here. The other thing is that sometimes if we encounter a Bernoulli distribution, we can make use of a built-in technique in JAGS whereby the Bernoulli can be construed as a binomial and thereby achieve a speed up. One of the examples, actually one of the exercises requires you to do that. It's a guided exercise, so you just need to follow the instructions and you'll be able to do that. So which is why we have converted a Bernoulli distribution, a conceptual Bernoulli distribution, into an analogous binomial distribution when we specified a model. And the third thing is we can perform the estimations of the posterior not just for the aggregate model parameters, but also we can make pairwise comparisons, which makes sense for us. So one of the pairwise comparisons we made was between a pitcher and catcher, and the other one was between a catcher and a first baseman, to see whether they differ in their ratio, in their batting efficiency, let's call it that. And we found that yes, they do, based on the specific posterior distribution and the values that we computed. Similarly, we wanted to see whether different batsmen batters I should say, who play at different positions, if they differ. In certain instances they did, in certain instances they did not. So these kinds of nuanced analyses are possible fairly easily by just specifying the appropriate requirements to the plot MCMC function. And we are able to do that because we have the posteriors computed for all of the individual players. So now comparing the difference of these two posteriors becomes fairly efficient. And we do all of that through code like this. And the specific things that we include here are really answers to the questions that we have. So if we had other questions, we would have probably come up with other kinds of analyses. So for instance, we could have a higher level category where we would define a position based on the proximity to the pitcher. So for instance, we could say, are certain positions which are very close to the pitcher, do people who play in those positions, do batters who play in those positions, have a higher batting efficiency than those who play in positions which are farther away from the pitching mound? We don't have the data for that in this data set. But what we could do is we could compute a third column over here, which defines the location, whether it's near or far. We can make it a categorical variable and say positions, first base, second base, and pitcher are all close to the pitching mound. and positions, say left field and center field or right field or whatever, they are farther away. So accordingly we assign values to that, and accordingly we set up our model and our summary functions to produce such results.